Good morning. It's a pleasure to have with us today Dr. Jiasheng Huang. He's a professor of the National Astronomical Observatories of China, of the Chinese Academy of Science, but also scientist of the US Harvard-Smithsonian Center for Astrophysics. He leads the cooperation between China and Chile in astronomy, and he will tell a bit about that at the beginning of his talk. Jiasheng obtained his PhD of astronomy from the University of Hawaii, where he spent six years. Then he moved, his first postdoc was at the Max Planck Institute for Astronomy in Heidelberg for a couple of years. And since '99, he joined the Spitzer IRAC science team at Harvard, at the Smithsonian Center for Astrophysics. He has been leading or participating in a lot of Spitzer surveys and very, very key surveys in astronomy these days, also in Herschel. And today he's going to talk about an unbiased ULIRG sample at redshift 2. Jiasheng and his wife have been visiting us for the last couple of days, so here the IOC, but also the observatories, the two observatories. And the idea of this visit is to explore possible future collaborations in astronomy, similar or not, different from the ones that China have started with Chile. So thanks a lot. Thank you. Thank you.
Hello, everybody. So I'm learning Spanish, otherwise I would have a short, brief address in Spanish, because my Spanish is not that point yet. So, okay, in the beginning I just talk very short about the China-Chile collaboration. So this is our center, it's called CCJCA, which is China-Chile's Joint Center for Astronomy. So the longer name is called the Chinese Academy of Science, South American Center for Astronomy. I don't like that long one, it's called CASACA, which is too long. So we started 2 years ago. This is the goal. So basically, China is somehow rather weak in observational astronomy. So one of the goals is to let the Chinese observational astronomy grow by access to the world-class telescope. And go Chile is clearly a important options for us. So we got fundings. And then the way to do that is we have to bring people from China to Chile. So that's why we set our office in University of Chile, the Cerro Calen. If you've been in Santiago, you know that's on the suburb of the Los Condos, suburb of Santiago. So that's our office, which the way we do that is we rented the office, but we didn't pay the rent. We actually hired a postdoc, hire a faculty position for University of Chile. So that way we can have this probably about 6 office free. It's not free, it's the way we pay. So we recently hired that postdoc from California, Chileans, and then he's happy to return to Chile. So that's what we do with it is, as I said briefly, that both sides agrees to do these things, and we support workshops. We also support the visiting scholars and the students, both sides. Either the Chinese students or postdocs come to Chile, or Chileans visiting scientists and postdocs come to China. And we also sponsor the workshop and the meetings, not just the meeting cost, also the person who either from Chile or from China who wants to go to the other side to attend the meeting, and we actually did it recently. So recently, this is the meeting we sponsored. One is the China-Chile workshop. 2 actually. One is Bio de Mar, which is it's on the coast of the Santiago. And the second one, well, fourth one actually be in Guangzhou, which is a big city next to Hong Kong. And we will also sponsor the 3 really the science workshop, which does not mean just China, Chile. It's also international one. I think we have the astrometry meeting, which is AD, I never pronounced that right, Adela conference in Santiago. And then there's a dense stellar simulation meetings, Modest 15 in Concepcion. And then we have a star formation meeting with Sponsor, which is in the Puerto Barras. Puerto Barras is a nice place. If you have a chance, you should definitely take a look. It's very nice. So there's a small project we sponsored, instrumentation project. We sponsored from our own fundings, the China-Chile Center fundings, which is one is this SON project. We hope that SON will have a small telescope settled down in Chile, and we're going to support part of their cost. And then this is upside down, so this should be first. So we signed lots of things. That's basically both sides agreed to do these things, and we signed a memo with the CONISAT, so that they can hire the postdoc for us. This China-Chile postdoc fellowship. CONISAT is the Chilean's funding agency, and then we signed a agreement with SOCHIAS, which is the Chilean's astronomy society, which makes sure that everybody is happy with this agreement, because some people worry that too many Chinese are going to come to take our telescope time. So this is things to make sure that everybody is happy. And we signed an agreement with University of Chile, so that they can host us, and we can put our money in the University of Chile's account, so that they manage our fundings. And of course, we signed a agreement with the Santa Maria University, which is the main campus in Valparaiso, but they have a campus in the suburb of Santiago, so that we have a relative large project going on, I would mention, in their campus. So now we have those Chinese who visit us and Chinese postdocs. You know, we among those postdocs, we have one from Mexico, a girl, Carla Alamo. And this year, we're going to have another 5 to 6 postdocs. Our postdoc is positions are not limited to either Chinese or Chileans. Everybody can apply. But the only requirement we ask is that you have to stay in Chile and China, not just Chile, because otherwise, you know, China will not benefit from this postdoc agreement. So up until now, we have 4 postdocs, and I think this year the CONISAT is on the changing, so it's a bit slow. I would expect that by the end of May they will have a call come out. So this is one of the instruments, search for extraplanet. The Chinese group is in collaboration with the Católica Professor Paulo Infante to try this instrument on the telescope in Chile. And we also participated in the Leo Brufman's sub-millimeter instrumentation group, and to construct some instrument for the ARMA. We invest bit money, and this is a kind of a bigger project that we put a quite big chunk of money from our pocket. It's about $1 million US. Up until now, probably we'll have more. Is we are building a ARMA center in Chile. We know that in ARMA center, you either in Europe, in Germany, not Germany, in Japan, in United States, and now we are building one for Chilean community so that they can use it. So last thing is that, well, China does have some advantages. If you are doing theory, if you are doing the simulations, and you can come to China, we have a very good computer systems, very large computer. And Chilean is not good in theory, so there's a lady postdoc, Paulina Osman. She come to China to use our computers to do simulations. And this computer simulation group in NAOC is led by a German scientist. Actually, now the NAOC is becoming an international institute rather than just full of Chinese. Don't worry, you're going to have coffee, very good coffee, and you're going to meet lots of people who do not speak Chinese. But of course, we are offering Chinese class, so at least you learn a bit to deal with the normal day life. So this is my summary. I just posted here. You can read. I can briefly answer some question about this China Chile Center stuff. Thank you. This is a short one. Either I can answer now or I can answer after I finish my science talk. Which way? I can continue. Okay. Okay. So this is my science talk. Talk about massive galaxy formation at z equals 2 through the ULIRG phase. So the goal. So the goal is that actually we know that since the scuba galaxy find, so we know that there are dusty ultraluminous galaxy at the high Z, but we also know the problem. The samples are small, and they are biased because you are looking at the one wavelength selections at the different redshift. You are looking at the different dust temperatures, which is later I will emphasize on this point. And your subliminal galaxy is biased towards the cold dust temperature. It's not the whole story. If you want to have a complete sense of ULIRGs at z equals 2, the subliminal galaxy only offers to you a look at a small fraction of it. It's not all of them. So how we do that? So these are other problems. For the subliminal galaxies, you have a problem to get everyone, get redshift for everyone, because usually they are optically faint, and you cannot get them. And it's substantial work. And Scott Chapman did it, but it's just a biased sample. It's optical bright sample, not mentioning there are a lot more optical faint one, even for the subliminal galaxies. So here I'm going to talk about an easy way to get a complete sample with relatively no bias. So back in beginning of the Spitzer, when Spitzer was just launched into orbit, we actually find an easy way to identify high Z galaxy by looking at the tracks, the color tracks, as a function of redshift. You noticed that let me see if that works. No. All the high Z galaxy are right here. So this is because why the galaxy behave so nicely along this track is because in the near infrared part of the SED, the galaxy in the near infrared band, the galaxy SED are more or less the same. They have a 1.6 bump, and then it drops. So we take advantage of 1.6 bump, and then to describe the colors. So this is another thing to show that how this bump works. This is all the galaxy, red galaxy, blue galaxy. If you know their redshift, you can normalize at one point. You see that whatever you have dusty or non-dusty galaxies, they are near infrared SED are more or less the same. This is you put all those redshift one together, and then you can test if that really works. Is by plot the one with the redshift. You know you have a redshift. You see that the galaxy population moves along the track. Here I marked the blue galaxy as the blue galaxy, red galaxy as the red galaxy. You see that the blue galaxy goes from the very red in terms of 3.6 minus 8 micron, and the red galaxy goes from quite blue this color. The reason is that at the lower Z, the galaxy 8 micron picked the PAH emissions. So the 8 micron flux is high. That's why the star-forming galaxy goes from up to the lower point, while the quiescent galaxy, which do not have a pH, it goes from that point to that. But when they get to the z equals 1-ish, beyond the z equals 0.3, you see these two galaxies start getting together. Eventually, at z equals 2, they are basically in these regions. So the way to do that is if you plot the 24 micron, all 24 micron sources in this color diagram, you see at the z equals 2 regions, you have a very strong clustering points, which means you got a lot. This indicated that 24 micron can select lots of z equals 2 galaxies. Is it true? So I'm going to skip this one. The reason for that is because this is the 24 micron profile. You consider that your pH at z equals 2, pH moves to the 24 micron band. So if your pH is very strong, 24 micron band at this point acts as like a selected the narrow band. It's more or less like a narrow band survey. Actually, you pick a certain redshift where your line shifting to your band. That's why how this works. If you just simply convert the 24 micron profile to the corresponding to the pH, and that's the redshift you get. You get peak at the 1.84. That's the best redshift you could pick using 24 micron. That's my point. So just we can select the pH with the proper IRAC color cut and the proper 24 micron flux cut, and you get a very good sample. And this is very similar to the narrowband surveys. And then we can do a very simple toy model to prove that. Is you take a galaxy, say up to 20. Well, it may not be the typical one, but anyway, we take that one. So you calculate the K corrections, and you assume a luminosity function. We know the local one, or roughly we know the high Z one. So then you can predict the redshift distribution for the 24 micron sample as a function. Here I plotted two samples with different flux, 24 micron flux cut. So, but basically give you the same idea. You see, you're going to have a very high, lots of lower Z1, and you get the peak distribution at the Z equals 1.8, and the color cut is just reject the lower Z galaxies. So, well, there's a new one. You can using 3 color, but basically it's doing same thing. Is it true? So we actually spend lots of time to confirm that. We picked the source and to do use Spitzer to do IRS spectroscopy. Basically, every sources we took with the IRS shows they are redshift at around 1.8, 1.9. That's the evidence. You see in this galaxy, high Z galaxy, you see the pH, 7.7 pH, 8.6 pH, and then at around 30 microns, the spectral is lower. This because this 10 micron silicate absorptions, and that's what you see, the lower spectra. And you even see the 11.3 pH in this spectra. This is all right. Beyond that point, it's getting noisier because the IRS the sensitivity is very bad at that beyond the 35 microns observed, and then you do not get the useful information. But here the basic point is that actually, if you take the selection what I just said, you go to the IRS, it just gives you all galaxies around 1.8. So that's the point, which confirms that our selection works. So this is another sample I want to show you, but here's an interesting point, is the one with the red dashed lines. And that one is not in our sample, but it's in the IRS slit. The reason I want to show you this is also at Z equals 2, but this is the very dusty AGNs. So you do not see pH. What you see peak around 25 micron is because you have very strong silicate absorptions upperposed on the continue. And that makes that peak look like a pH. That actually is not pH. But this galaxy, if you look at the IRAC color, they have a power law ACDs, and then our color selection will reject this galaxy because the power law is on the red corner of that diagram. So that galaxy will be rejected. Why it's in my sample is because it happens to be in the long slit, in the other end of the slit. So we show this to prove that actually there are also other dusty Z-2 galaxy, but those are the AGNs without pH. So there are other people who do the same thing. There's Ling Yan and Fada's sample, Jim Hawk's sample. Basically, they did similar things, basically. So we tried on the ground-based telescope to measure the redshift with the optical and the near-infrared spectrograph. This is one on super. It was not very successful because it's very dusty, and basically the line we do not detect lots of lines. This is one exceptional one. We see the H alpha. You see the IRS give you a redshift of 1.992. The near-infrared H alpha gives you 2.03, which is more or less similar. But the point here is that the IRS redshift has a large errors, probably 5%. So which may not be good for the SEAL detections. But it's good enough for it's much better than the photo Z. It's good enough for the statistics. That's my point here. So other people did tried really hard on the 10-meter class on those galaxies. You see, they get some redshift. This is one of the plot I showed. So basically, unless you happen to have an AGN, you have an emission line in the UV band. Otherwise, you do not see many lines. You see some UV absorption line, like magnesium-2 lines. That's about it, and that's a very tough business. But the point here is actually we just proved that we do not need this if you just want to do statistics and you have a very nice sample. So there's a bit physics if you just play with the IR spectrum. You stack all the high Z1, which here is a black one, and compare with the local ULIRGs, which is we stacked according to their properties. We have a liner type, CFA2 type, and the H2 type ULIRGs, and then the LIRG or starburst galaxy spectrals. Basically, you see that CFA2 has a slight higher continue, which we understand that because of the AGN contributions. Otherwise, the rest 3 type, the H2 type, the liner type, or the starburst LIRG type galaxy are more or less have similar IR spectra. And our Z-2 is very similar to these 3 types except the type CFA2. This somehow indicate that most of our galaxies are the starburst dominant ULIRGs. But that does not mean that we do not have AGN in our sample. And we found actually about 4 to 5% of our sample have X-ray detections. This is a bit controversial. And in the beginning, we think the X-ray comes from the star formation. You can easily convert X-ray luminosity to the star formation rate, which is similar to what you get from the infrared luminosity. But some people argue that why, if you can do such conversion, why you only get 4% or 5% X-ray sources? Why not all of them? What not even 50% of them? If something happens, by look at the X-ray hardness ratios, there's some indication actually those X-ray detected one may be just X-ray, but maybe they are deeply buried in the dust balls, and you have some chance to see through some angles. So point is that if you look at the infrared properties, you will not be able to say that those are the AGN by looking at the spectra. But again, there are 4 to 5% of this galaxy are actually X-ray sources. They may be the X-ray AGNs. So during the Spitzer code mission time, lots of group is doing similar things. So this is the redshift they got. Basically, you see that they are more or less sampling the same place. Here we compiled all the redshift here, which is more or less similar to what my toy model predicted, which is peaked at 0.8, 0.9, and spread from 1.5 to 2.5-ish. So with this selections, we can do a large sample without spectroscopy. We know they are at the 1.8 redshift of 1.8. We can select, use these color selections, use this flux cut in different deep Spitzer survey field. Actually, we have a Bootes, which is very large. We have Cosmos and all this famous field. We have Swire. So this is our samples. This area, this is the Z equals 2 number of Z equals 2 galaxies according to my selections, and this is the flux limit. We have a slight higher flux limit for the Swire field. The reason is Swire is kind of shallow. So we also compare our selection with the Cosmos photo Z sample, and we grabbed all the photo Z sample and matched to our sample. Actually, you see the Eobet's photo Z is confirms that our redshift is around in this range. Of course, their photo Z for this particular sample may have larger scatters because in most of the case you do not have a very bright optical band photometries. So here's number counts. First you do is number counts. Basically, you see you have a rather larger scatters, which is reasonable. I will later argue this galaxy are the massive galaxy. They suffers large field-to-field variations. But if you go to the Swire field, they start to deviate from this distribution. The reason for that is the Swire field, the IRAC photometry is shallow, so that the color selection somehow failed to pick some faint sources. So you do not, you start to losing galaxy at the faint end. So of course, we wanted to know what is the FIR detections, and most of the galaxies are detected by Herschel. So no problem. This is the 24 micron contours put it on the Herschel imaging for our sources. Basically, the brightest 24 micron source in this diagram are our sources. So you see they are corresponding to the Herschel detection clearly. So this is another one. I'm going to when Herschel was just launched, and George Magdas, and he was Dimitri's student, and then mine. So he did work by fitting the FIR SCDs. And here's the point, is that he compared the dust temperature with the SMGs, and this is a very interesting, very important argument to say that we have a fair sample. You see that the red dots is our sample, and the blue shadow region is the SMG. You see SMG, you sort of see correlation. This is not actually correlation. This is because of the selection effect. Is because if you look at the high redshift, 850 micron will shift it to the rest frame of the will sample the rest frame of short wavelength band, which you intend to pick the hot dusted galaxies, while the low redshift one, you look at the longer wavelength, you are picking the cold dusted galaxies. That's why you see these correlations. And of course, there's a redshift effect in it, because the high luminosity one would add the high redshift, so that they have a hot dust temperature. That's why you see these correlations. And then you see our one do not have such correlation. The reason for that is we do not know the FIR properties. All our selection is only associated with pH luminosity. That's it. We have no more others the criteria superposed on our selection effect. So that's why we do not have a dust color selections. You see, by look at this, you see what the SMG missing is the hot dust ULIRGs. You will not be able to find the hot dust ULIRGs using submillimeter selections. So, And of course, you want to know the FIR to the 8 micron. This is kind of sort of very good correlations with certain scatters there. And this is refined actually. And then since we know the redshift, so we can do the luminosity function. And then this is the 8 micron luminosity function plot against the local one. So local one's easy. You get the redshift, you get the 8 micron photometry, you get the local luminosity functions. You see there's a 2 magnitude evolution. And this is not surprising because we know the Mador plot from z equals 2 to z equals 1, there's a big star formation density changes. And then that evolution reflects that changes in star formation densities, which is not surprising. And the other thing is that the Carina Caputi, using photo-Z to do a 24 micron luminosity function only in Goods field, Goods North field. And see, it's, her result is nicely consistent with ours. It's very nice, actually. So, on the other hand, you see that this selection only allows us to select the luminous part of the galaxy, not the faint end. So, of course, you compare with the different type of galaxy in terms of star formation densities. You know that at z equals 2, these are dominant. The ULIRGs are dominant. This is also known, but this time we're actually using number to pin down this. Is at z equals 2, the star formation rate density rate is dominant by the ULIRGs. That's for sure. So people always ask, what about stellar mass? Yes, we are doing that, but it is difficult because it has a very complicated star formation histories, as I indicated later. So if you fit the ACDs, it's nice ACDs, you probably get stellar mass of above 10 to the 11th, which is very dusty. The fitting star formation rate is about 200 to something bigger ones. Not here. This is like, yeah, it's around 200 solar mass per year. You could get a high one. The problem with this stellar mass function, stellar population fitting is that we know that there are lots of young stellar populations in these galaxies. That here's some hint that you see 1, 2, 3, 4. About half of them, 8 micron, is higher than the model prediction. And at z equals 2, 8 micron is the rest from K-band, and which means the K-band is brighter than what you can get from the model prediction. There's a reason for that. We know there's AGB stars, and then there's a argument that the Maraston model would fit this type of galaxy better. But I think the situation is still a little bit complicated, and I would be very cautious. But some people argue, say, forget about the near infrared. If you want to get the stellar mass, you just fit to the 4 microns, you probably get the right answer. And then even here, that the fitting does not match to the 8 micron. It knows that 8 micron is high. It's okay. Maybe stellar mass is reliable. Maybe. So I have to still be careful. What about K-band luminosities? Here's the K-band luminosity, because you can derive the K-band luminosity function compared with local K-band luminosity functions. You see that at z equals 2, K-band luminosity is much higher than the local luminosity function. This is not a stellar mass evolution, because we know that at the z equals 0, the stellar mass at the bright end should be higher than z equals 2. This is another evidence that the K-band light probably consists of more than we just know, probably a strong AGB phase, which boasts K-band luminosity to a high level. That's why you see the K-band luminosity function for this particular sample is much higher at the bright end than the z equals, local or lower Z1. So that's enough. So the other thing is we stellar mass star formation rate relations, specific star formation rate relations as a function of stellar mass. This is kind of normal things. Basically, you see this population is similar to what we see from other sample. Most of them are the so-called normal galaxy, with a few above this relation, which we know people suspect they are the fast evolved galaxies. So this is another thing I think that's interesting, is for the first time you actually can study the 2-point correlation function for these ULIRG samples, and we got lots of them. This is one field I show you. It's a very large field. It is the Buddhist field, actually. You see that I marked the galaxy with different size. The large size means the luminous one, faint size. The small size means the faint one. So you see, by eye, the bright one are strongly correlated, actually. It's very easy to measure the 2-point correlation functions, is because you can do the angular correlation functions, and then you know the redshift distributions, as I said in the beginning, because we already know they are how they're distributed. So you actually can get the 2-point correlation function for this sample. So actually you can measure the bias, and you convert bias, and their volume densities. You know they are means. This is wrong. Sorry, my student did it. Suppose 10 to the 12. You can get the mean halo mass for this population is 3.5 times 10 to the 12 solar mass. So this is the first time we know what kind of halo these ULIRGs resident. So this is kind of measurement only possible with the large samples. So this is we can put this in this diagram, which this is a quite popular diagram, how the halo mass evolves, consists with correlated with the galaxy we see in observations. So where are we for this sample? Is here. Oops. Yeah, here. It's very high. The bias is very high, which means those galaxies, if you believe this track, will end up to be more than 6 L star galaxy in today's population. So the last thing I want to talk about is morphology. Oops. Morphologies of this sample. So in the beginning, when the Spitzer's only optical imaging, the ACS is available, we look at we got the time, we look at this population in some field. So it's inconclusive, because if you look at this optical, the ACS I Z-band image, and at Z equals 2, this galaxy, this band already sampled the UV or far UV. So it gives you very spotty or clumpy morphology. You don't know what's going on. You even have a right angle. I don't know what. This is because you can imagine you have a galaxy with lots of dust distributed ununiformly, and you only see part of it. That's what the part of it you are seeing. And you cannot get the whole picture of it. So up until candles, we start to get some idea. So here's a very good example of compare the ACS image with the candle image, which is a near-infrared image. You start to see, you get nothing or 1 point or 2 points. You start to see this 4 type of galaxy we see in near-infrared. One is the multi-clumpy morphologies, the first one. The second one, it's surprising. It's a very regular morphology for a galaxy. You see the disk, you see the bulge, this galaxy. It's very interesting. And the third type is the lower surface brightness one, which it shows here. And then the last one is a merge. You can see 2 galaxies are crash with each other. So this is further information. I mean, we put a stamp image from the U band, which is 436 F4635 W435, all the way to the H band, which is F16W, and this is B band or U band, G band, I band, Z band, J, Y band, JH band. So you see that the morphology become more clear when you get to the near infrared for this type of galaxies. So I'm going to show you some nice picture. So we found most of them are actually, if you have this near infrared, are the merge or the lower surface brightness one. This probably is also merged. There's another bright one there. So, but in some case, you still get the spiral galaxy. Clearly, it's a spiral galaxy, even though it's ULIRG. It's spiral galaxy, another spiral galaxy with bright core. My explanation is maybe the high star formation. The most of the infrared luminosity comes from the center. You see, the center is very bright in terms of colors, and you got lower surface bright one, and you got some multi-clumping one. So there's another one. So again, you see the spiral galaxy, and that's probably a spiral galaxy, and then the rest of the merges. So that's my current status of these populations. I leave my summary here. So basically, the point I already made in my talk. So thank you to attend my talk. Thank you.
Thank you so much for this interesting talk. Now we have time for some questions, in case there is any of them.
Could you comment on the metallicity of these galaxies? I mean, they are dust rich, so
yes.
It means that they have to be fairly metallic. But
right. But with no spectroscopy data, cannot do anything. We have to assume they are solid. That's all I can do.
But there are no measurements of.
Sorry?
There are no estimates or measurements of this metallicity.
There are only few spectral for these sources. So they have H alpha detections. For this, the H alpha detection I showed here, I wanted to see if I can detect O3 or O2. No detection because of dust extinctions. So it's extremely hard to do this.
Sorry, when we compare the local ULIRG SDSE of the local ULIRG with the high redshift, I mean the Z equal to 2 ULIRG, so you showed it in the picture. So I was wondering that's why we don't see a kind of shift in the peaks when we compare these two cities.
Hold on. This one, right?
Yes. So shouldn't we expect a kind of shift in the peaks, in the lines or the features of the CD?
Oh, you mean
when
the
we
redshift?
compare? Yes, when we
Oh,
compare.
I shifted them back so that I
okay,
can have
so
nice
you correct.
comparison. No, I shifted them back.
Okay.
Of course, the local is A micron is A micron, and at the Z equals 2, the A micron is supposed to be 24 micron. These numbers, except that the wavelength is real, the flux is not real. It's just I normalized at the peak of the 7.7 micron, so that I can have a nice comparison.
Okay. Okay. Thank you.
Please.
Yeah, and also related to that figure, I didn't get very well why you were surprised by the percentage of AGN that you detected in these sources, because it's known that ULIRGs have a relatively high percentage of ULIRGs have AGN, right?
Yeah, I know that, but the point here is by just look at the IRSM spectra, can you tell if this galaxy are AGN or not? But at least what I compare my Z equals 2. If you don't have the local one, you have no idea what you get. With the local ULIRGs, and the first idea is which of the spectra would be more similar to what I see at Z equals 2. That's the beginning idea. And we know that later I say that maybe there's AGN buried deep in the dust balls. You cannot see it, which here shows here actually. Those AGN do not affect your IRS spectra. That's probably the point I want to make. Well, I agree. I mean, there are AGNs in the center, of course. And I said there's a project going on is we're going to do the all X-ray detected ULIRGs, this type of ULIRGs, because this selection does not actually is biased against the AGNs, because we know that we have a strong pH And then pH usually does not get along with AGN. Yeah. So we actually have a large sample, and we match our sample to the Chandra deep field and other Chandra field. We found there's more, something like 100 sources with the X-ray detections. We're going to look at their morphology, we'll look at the other property to see what happened there. So yeah, I agree with you. It's this does not mean they do not have AGN. It just say that their IS spectra is similar to what we see in the type of ULIRGs locally.
Yeah, can I come back to your first talk about the collaboration with Chile? I was wondering whether you see any possibilities of doing something similar with us here in the Canary Islands, and if so, what kind of form it would take? Would it be similar to what you described for Chile?
Yeah, yes. Yesterday, the day before yesterday, I talked to the FIR, your directors. Yes, I actually, since I know quite a lot of Spanish astronomers, I personally very interested in collaborating with the Spanish on astronomy, and currently I think the China-Spanish collaboration is lack somehow. I don't know why, but compared with the China-France, China-Germany, they have regular meetings, and they have both sides put money in these collaborations. And I think this is one of my goals come here to link this community together. And what I proposed yesterday, the day before yesterday, is we should have more visitors. We should have organized a two-country workshops to let two communities know each other, so that we can start these collaborations. So, I mean, in the past, most astronomers in China are theorists. So they are probably, it's not the exact same field that Spanish focus on. So now more and more people like me have a observational astronomy background return to China, and I think he has a great opportunity to participate in GTC or other telescope in this island. So I think it's a great opportunity for us to collaborate with Spain, especially you guys. So I love Spain, myself actually.
Okay, well, it would be great if that succeeds. Then going back to your scientific talk, well, thank you, because it was very, very nice. And also it's interesting to see how many interesting things you can do using these databases if you know how to use them.
Right.
But going to the last point in which you talk about the morphology, I'm not sure what is the issue there, because in the image you first mentioned that with the cosmos images there was somehow clumpy or smoothy, or I mean spooty or whatever. But it is also true that this is set equal to, then every one of these spots that you are seeing there is quite a big thing. So it's something different what we have in mind when we think in clumpy galaxies, in which you speak about a spot of, I don't know, say a few hundred parsec size. These spots must be very big.
Right.
And also all the things that look like spotty must be the signature, as you said, of mergers or things similar. So, and then when you go to the candle image, which is, as you said, clearly much more different because it's smoother and so. But it is also clear that when you conclude that you don't see many signs of disks, in fact, at this distance, what you would be able, as you know, to identify as a disk would be a very big disk, right? So, but and I think this is important because in the sense that putting these objects in the context of the galaxy evolution, which is the thing you are doing, right? It is there are things which are maybe a bit misleading, because I mean it is true that you cannot identify big disk, because I also wonder how would this big disk survive if you have such a strong mergers as you will probably have, and also I mean the disk of galaxy, the normal galaxy, which are, I don't know, 5 kiloparsec size or something like that, we will not be able to see at this distance with these images. Am I right?
Right, you're right. Well, I think the point is that point I made in my talk is actually in the beginning when we just have Spitzer, And then we look at all the optical images. We have no clue what they are. I mean, just dots. And then you have it near infrared, and the dots are connected, and it changes. That's the whole point. I mean, so and the other surprising is that, as you said, the disk galaxies. And I mean, in the beginning, we asked, in the ULIRG, do we expect to have a disk? Right? We do not. Locally, we do not see the disk galaxy. But at the high Z, you start to have a disk galaxy, even with such high star formation rate. And that's something new, actually, we need to understand. That's my point. Yeah.
Yeah, coming back to the questions of morphologies, have you quantified the number of different morphologies you have, like compact galaxies or versus disk galaxies, or and also have you measured sizes, or do you have any clue on that?
Yes, actually, one of my students did it. I didn't mention it. I forgot. We have measured the Gini 20 and the Gini and the M20, and then we have this measurement. I just didn't have it in my talk. Yes, we did it. Yeah. There was that's one of the study we want to do, is how we're going to define the disk galaxy. I mean, this using eye may not be the objective way. So that's why the digital morphology is the way to go. So.
Oh, thank you for your talk, and I hope you have enjoyed your visit yesterday to the observatory and the GTC in particular.
It's great.
My question is returning to the collaboration China-Chile. At which extent, from your opinion, that collaboration has generated from the Chilean government new resources for astronomy, or that collaboration is just supported by the own resources of the different universities?
I'm not sure I understand. So can you
that collaboration has generated new money for the Chilean astronomy from the Chilean government?
The collaboration?
Yes.
You mean the China-Chile collaboration?
Right.
The only in astronomy, first, the money comes not from Chilean government. Most money comes from Chinese government. So the CONICET may match a bit in terms of postdoc, in terms of supporting meetings. Other than that, they do not have a specific fundings, say, they can be used for the China-Chile collaborations. So we have a budget. I just told Ismail that this morning I want to have a detailed budget diagrams here, but I didn't get it this morning. So the annual budget for this collaboration is about $2 to $3 million US annually, and which I'm not happy with it. It's not like money is too little, it's a lot of money, but that amount is not enough to do big things, but each year we are pushed to spend it. Otherwise next year they say, you cannot spend it, why we give you more? So we are in such a weird way of spending money while we cannot do big things. So that's why we are struggling with the Chinese government, saying, look, we cannot do this. We have to have a big picture and a longer term plan rather than just do year by year. So that's the current situation. With the, say, $2 million US, we can do all this people exchangings, postdocs, no problem at all. But it just cannot do big things. So that's why Chilean government does not put any money. So we already have enough.
So let's thank again for the interesting talk.